I'd like to introduce Chris, who will be speaking on full system emulation, achieving success automated dynamic analysis of evasive malware.
Thanks for the intro. All right, so thanks for the introduction. I'm talking to you about dynamic malware analysis and the challenges that we face when doing so, as well as potential ways in which we can circumvent, work around those challenges that the attackers throw at us. Before I get started, just 1 minute background. What's my basically way up here? So I'm currently the chief scientist and one of the co-founders of Lastline. Lastline is a company, a vendor that works on providing solutions for advanced threats and advanced malware. And it really started out as an effort to commercialize some of our work, some of our efforts that I was involved in previously at the university. So I'm having an academic background. I'm currently on leave from the University of California in Santa Barbara. And some of you might have heard of the Anubis and the WebAwet systems, which are two systems, one for the analysis of malware, the other for the analysis of exploit kits and JavaScript in malicious web pages that really sort of were driving our interest and our work in this area for many years. So what is this talk about? I want to talk about automated malware analysis. In particular, how can we implement an environment that allows us to analyze programs, unknown programs, and to detect if they are malicious, as well as to provide forensics information that helps us to understand what types of malicious activities programs might be involved in. And basically, I'll talk about different ways in which we can build these systems, and then want to highlight one particular threat, which is evasion and evasive code. Because, of course, in security, we typically face an arms race, and when we try to build better systems that allow us to detect more malware, that allow us to detect more sophisticated malware, of course, attackers react to this, and they want to make sure that our job as defenders is becoming harder and they can fly under the radar. And evasive threats are a particular problem for dynamic analysis environments like sandboxes, and I want to spend some time on just telling you a number of ways that we have seen in which attackers try to identify and bypass detection and analysis in sandboxes. But I don't want to just stop there. I actually want to end on a more optimistic note by telling you some ways in which we believe that we can build some counter measures in which we can maybe combat entire classes of evasion and find ways in which we can turn the table and maybe use the fact that a program tries to launch some evasive behaviors as an additional signal that actually allows us to detect that it's doing something bad. So these are sort of the three different parts that I want to talk about. Let me just set maybe spend 2 minutes to set the stage. Why do I believe that automated malware analysis is important? It's really the result of two trends, and I'm sure you have seen one of these slides, in many talks or in many different forms. It basically shows that attackers have moved on from just hacking for fun to hacking for profit to even hacking to obtain intellectual property or state secrets. And as part of that evolution of the threat landscape and malware authors have become more sophisticated and can invest more resources to target malware specifically to a particular organization that they want to attack. And when you target something, then it becomes very difficult for a defense solution that relies on having seen a particular malware somewhere else to be creating a signature to actually have a signature for that. So the fact that it's being targeted makes it much harder to rely on traditional signatures and on reputation information. But they also are more sophisticated. That means they can invest in, of course, reconnaissance of the target, but also in crafting malware that is using tricks to evade a sandbox that the defender might use. So that's one problem, the evolution of malware to becoming more sophisticated and more targeted. But also there's the problem that there's really a lot of malware out there, and it takes a long time to do manual analysis. So, If you have done work on malware analysis, you might have seen, you launch it in a debugger and you use a number of system tools to analyze maybe the processes or the network traffic or the registry keys, and it takes you a long time. If you're working in incident response or if you're working in manual reverse engineering of malware, it just takes a long time to understand what malware is up to and what the capabilities of a piece of malware are. And if you combine that with another graph, I'm sure you have seen tons of times, sort of this exponential growth of the number of threats, then we can really see where the problem is. There's a lot of malware, and it takes a long time to analyze it by hand, and it becomes more sophisticated and more targeted. So we really ought to have some mechanism, some general technique that tries to put something against this threat. And a very important class of tools are sandboxes, dynamic analysis environments. I just want to sort of give you a little bit of a stepping aside here, side note. We are mostly talking here about the analysis of the classic Wintel x86 malware. Other malware, for example, those written for Android, might be more amenable to static analysis because, it's no longer code that can, write new instructions during the runtime, deobfuscate itself. It's much harder for malware authors on a Dalvik environment to use a lot of these obfuscation tricks that they use to combat static analysis for x86 binaries. So we're mostly focusing here on sort of the classic malware that is written with the idea of running on maybe Windows or Mac for the x86. And for those, a dynamic analysis environment, a sandbox, is really, in my opinion, the best, most powerful option to understand what such a program might be doing. And the general idea is simple. You basically take the program and you run it, and you observe what it's doing. So you need some kind of instrumentation, some instrumented environment in which you can safely execute the program, and you need ways to observe, ways to understand what this program is doing. And the fact that you can do this in an automated way is great because you don't have to spend manual labor. So we can stem the flood, we can scale up to the number of samples that we receive. But, and that's also, I think, a very cool advantage that leads more and more security vendors to embrace sandboxing, it's the ability to handle a targeted or a previously unknown attack because you don't need a signature. You don't have to have seen a particular program before. You can make the decision on the spot. You run the program, you see in a very generic way if it's doing something bad, and then you can flag this program as malicious even though you might not have seen it before, or you might not have seen the source as being suspicious. So that's great. Let's talk about different ways in which you can implement it. We said it's an instrumented environment that wants to monitor the activity, the operation of programs. So what can we monitor? In the simplest case, we just monitor persistent changes to the operating system. After the execution of a program, is there a new file? Did that program create some network traffic that we want to analyze? So you get high-level information of a sample has been written, or some network connection has happened, or a registry key was created or modified. And in principle, that is really the very basic sandbox. Would be simple to implement. You can actually even use a bare metal, sort of a normal operating system, nothing special, no special instrumentation. You can basically run the program, and after the program has stopped, or after you terminate the program, you just look at the changes that have happened to the file system and the registry, and you can of course observe the network traffic that is produced. It's easy, but it also doesn't provide you a lot of visibility. You don't have any visibility into temporary effects. You might not have any, you don't know if files are being created and then deleted. You don't know in which sequence certain operations have happened. So it's typically considered not enough visibility. So you want to dig deeper. You want to see the interactions between the program, between that malware, and the operating system when it's being executed, right? So you see maybe an open system call, and then the program reads from that file, and then it writes somewhere else, and then there's some network traffic, and then it deletes a file. So you basically get a sequence of operations, and you have a much better visibility into the interactions of that program with its environment. And I would argue that that actually this is the way most sandboxes work today. It can be done by instrumenting the operating system. You can hook system calls, you can install a driver at the kernel level that records this operation between the program and the operating system, or you can instrument libraries in DLLs or the runtime, and you can basically say whenever the program invokes a system call, whenever the program asks the operating system to do something, then I want to log the information about this operation, maybe with parameters, and I want to learn something about this operation. And you can quite easily run something like this in a virtual machine. So you spin up a virtual machine, you instrument the virtual machine, you run the program, and you get a trace of the system calls. So visibility is clearly better. You see sequence of operations, you can see temporary actions, but I would argue that you still don't see enough. You cannot really see deep into the program itself. You don't have deep visibility into, okay, the program has read some information from a file, but what does it actually do with this information? Does it process it? Does it encrypt it? Does it send it over the network afterwards? You don't really know. So you're lacking visibility into individual instructions, you lack visibility into possible data flows, and that's really a problem, right? You would really like to sort of not just take the abstraction of, here's the program, it's a black box, it does something with the operating system, it's good information, but I argue that you want to look deeper. You want to have information that tells you how a program might process inputs or how outputs are produced and which checks are done inside the program, right? I mean, there could be compare instructions, there could be data manipulation operations that you just don't see when you just have the visibility of the operating system interface. So, given the same trace as before, if you look deeper, you can see, for example, hey, does the program leak information over the network that it has previously read from this specific file? Or does it, read certain bits of the registry only if it has previously received something from the network, maybe a command that triggers a certain activity? Or, for this write operations, where does the data actually come that is written to this file? Is it previously downloaded in the form of a download and execute, or is there some information that was statically embedded in the binary? So a lot of extra information that are lost when you just look at the operating system interface. So one way in which you can get that information is by using some kind of debugger. You just debug the process, or maybe more commonly, you use a small CPU emulator. You're basically emulating the CPU, you're emulating the individual instructions, and you have written some stub functions that basically emulate what Windows would do if a certain system call would happen, right? So if the program says, open this file, then you have a little emulator that says, okay, the file is now open. Or if the program reads and says, give me the first 10 bytes of this program, then your little emulator, your little process emulator can tell you, okay, here are 10 bytes from maybe even the real file or some emulated file. And sort of this visibility that you now have is, since you're emulating the individual instructions, you actually see every instruction that the program executes. You can understand what happens with data that is being read from a program, from a file, and then processed by the program. You might be able to understand what data is being sent over the network. So in principle, this is, in my opinion, an improvement, but it has a problem, and the problem is that the way these sort of process emulators are being implemented, they lack what we call here fidelity. They lack in the sense that when the program interacts with the operating system and you have basically emulated the operating system, so you're not using the real operating system, you have just written some stub functions that try to mimic some of the things that the operating system can do, then you're basically incomplete. It's likely, and we have talked to people that use this kind of approach, that a good fraction of your malware is not executing properly just because you would have to faithfully emulate the entire Windows system to be able to give the malware or any program that interacts with you all the information in a completely faithful way and in the way Windows would do, right? So you basically have nice visibility, but the problem is that your environment is not realistic enough. You basically had to spend a lot of work to writing this process emulator, and you emulate Windows, and it's not complete just because Windows is so big. So is there a way that you can actually get all the details while maintaining what we call here good fidelity? Basically, while maintaining the actual operating system and basically have the process emulated so you can see what the process does, but when it talks with the operating system or when it sort of interacts with Windows, why not just, emulate that too? Why not emulate everything, right? So the idea here that we are sort of wanting to distinguish or get at, you could implement a full system emulator that emulates the entire system and emulates the system not at the operating system level, but emulates the hardware, the physical CPU, the physical memory, so that you can run a real operating system inside your full system emulator, and you can selectively then say, okay, here there's some operating system code that's running, I just let it run and I don't really care about it, but hey, now the process that I care about is executing, so I switch into a detailed look mode and I know exactly what this process does, what instructions it executes, how it manipulates data that it reads, and how it creates maybe files or data that it sends over the network. So we basically get good visibility and good fidelity. The only problem is, since you now run a real Windows and the process that you want to analyze on top of an emulated hardware and full system, it might not be as fast as a VM-based system. So you have to be careful with that. And you have to be careful that your emulator has enough fidelity to be able to emulate the actual x86 processor and the physical hardware that Windows needs. But if you can pull this off, then we're sort of arguing that you get a visibility that instead of just giving you point visibility for every system call that the program might do, you actually see the entire instruction stream. And this extra visibility, as I will argue hopefully in a bit, is really crucial to do a number of things that are typically not possible without this visibility. So just, to recap, we're sort of having these two axes, visibility into the process, fidelity, how realistic is the environment for the process or the program that you're running, and you have high visibility but low fidelity with process emulation. You have high fidelity because it's a real operating system, but low visibility with a classic virtual machine-based approach and system call hooking, and we think that full system emulation combines both advantages. So, we have believed that for a long while. Actually, that's why when we started the Anubis project about 10 years ago, this is really the route we went. We started to build our analysis system on top of a full system emulator, and of course, when we later decided to commercialize our research, we built our analysis engine also following this paradigm. So, let's focus on what I said before. Why does visibility matter? I think visibility matters because first you see more behaviors. I hope I sort of already made the argument. I give you a few examples why this is important. But also, it really helps you when we talk about evasion. Because evasion are often little tricks or little checks or little triggers that happen inside the program and that ensure that the process can decide, hey, am I running in an analysis environment or not? And if you don't actually have the visibility into the program, then you just don't see those checks. You don't see those triggers that the malware might try to launch against you. So we argue that it's really important to see into the program when it's executing to be able to combat evasion. All right, so before we go to evasion, just a couple of behaviors that I want to point out. It might be interesting for you to understand from all the registry keys and programs and files that the malware has touched, which ones does it actually leak over the network? And more so, what are the network connections over which it leaks the data? Because it could very well be that the malware connects to 10 remote servers. And some of them might be decoys, some of them might be legitimate machines. So what are the actual destinations that are used for command and control and where the malware sends data to? That's an interesting thing you might want to learn. Another interesting thing you might want to learn is if data is read from the network, Is it used to trigger commands in that program? Does the program read commands from a CNC server, and what actions do they trigger inside your program, right? Again, you want to have this data flow information that you can say, data was read, and the program had checks inside that acted upon the data that it has just received. We can also, detect more about keyloggers. They're often passive in the sandbox, so if we basically have a fake user that enters information, then we can track how the program might hook the keyboard and might process the data that the user enters. Or we can take memory snapshots to aid static analysis. So the idea is basically to say, hey, this program has unpacked some parts of its code. It's now running some parts that we haven't seen statically on disk. Can we just take a snapshot of that memory image? And since we have full control over the process, its instructions, and the memory, we can basically take the information and we can then export it to something that someone can inspect in IDA in more detail. Okay, and so what I just said is sort of summarized here. We can detect keyloggers not only based on the fact that they hook system calls, right? Because they might use set Windows hook or get asynchronous key state to understand, if someone is typing something, but we can actually track how the data that the user types or how data that enters the process by reading these keystrokes, how the malware processes it. And that allows us to do things like, determinations like this, where then we can say, hey, we've seen that there's some stealing activity going on. The process not only hooks keystrokes, but it takes that information and maybe sends it over the network in maybe an encrypted form. And then we can tell you also what kind of data has been leaked. Or when I said before, supporting static analysis, we can recognize interesting points in the execution of a program. We can take a snapshot of that memory and then export it into IDA. And a user can just say, okay, a number of analyses have happened. Export the process snapshot, and then you see on the bottom of that slide, this is just the classic IDA view. You can basically see new untrusted memory regions that the program has created while it's being executed, right? And so all these things come from the deep visibility that we have into the process, and is often not visible when you just look at the system calls. All right, so let's talk about evasion. Of course, the malware authors are not stupid. They're seeing, hey, there are all these vendors that put in sandboxes in their products, and they can detect my 0-day. That's bad. So what they want to do is, of course, they develop code that detects the presence of a sandbox when being executed. And the cool thing is here, they can do that because a dynamic analysis environment actually runs the program. And so you run the malware, so the malware has a chance to do things like looking around, finding out, hey, I'm being monitored, let's just drop everything and pretend to be good. And then the sandbox doesn't see any malicious activity and thinks, well, that's a legitimate program, let's just forward it. And then it runs on the actual victim system and might behave very differently. So it's a big problem. How can you achieve evasion? There are three big ways in sort of our taxonomy here. One is you can detect the underlying runtime environment. So what I mean by this is, let's say, we use an emulator, others use virtual machines. Can you detect the presence just of an emulator or a virtual machine? Are there certain hardware differences? Are there timing differences? Are there certain artifacts being introduced? The second way is by not saying, I want to detect a generic runtime environment, but you say, I want to detect a specific sandbox. Maybe I know something about the sandbox. What kind of files does it create? What kind of other artifacts does it introduce in the Windows system? And I just look specifically for them, and if I find them, I know that I'm being analyzed. And the third thing is, you don't actually try to understand if you're in a sandbox or not. You actually want to make it so that the sandbox doesn't see your malicious code that you're executing. So you don't care if you're running a sandbox or not, as long as you can execute code in a way that makes it invisible to the sandbox or doesn't trigger it for a sandbox, then you're good. Right? So this is sort of the 3 points, and I'll give you a lot of examples for those in a second. I just want to show that this is actually real. So this is, for the Anubis system, the university system, you know, there's a malware packet that has an anti-Anubis switch, there's a crypto that has an anti-Anubis switch, there's another malware generation tool that has an anti-Anubis switch. So, you know, the attackers are well aware of our systems, and they create malware generator kits that already come pre-shipped with some code that tries to detect Anubis and also other sandboxes. So it's a real problem. Okay, and that's why we think it's really important, because it's not just a theoretical issue. It already happened, you know, a few years ago against our academic system. So you can imagine if you are someone who writes targeted attacks and you have the resources, you will certainly also study commercial sandboxes and try to evade them as well. All right, let's look at the different ways in which you can detect the runtime environment, and then I talk about how to detect specific sandboxes, and then how you can evade code from being analyzed. A classic way to detect a runtime, and in particular a virtual machine, is the fact that when virtualization, or also when emulation is being introduced, there are differences between the real hardware and the emulated hardware, or the virtual environment that is being generated. And you know, a long time classic paper already in 2000 and understood that there is some difference in the way privileged operations are handled, and when you are sort of in ring 0 and ring 3, and that allowed you know, a large number of little tricks that looked at how instructions are different, including the famous red pill snippet that allowed to see that certain addresses were different in a real Windows environment and then on a VM. Of course, you know, with the advent of hardware-assisted virtualization, for example, Intel VT, this went away, or these differences shrank substantially. So this is getting increasingly harder, because hardware is now making it more and more difficult for a program to understand if it's being run inside a virtual machine or not. But it remains a problem, and there are CPU bugs. For example, you know, Intel publishes bugs in their CPU, so sort of behavior that is not according to the specification. And if you basically run a test, then you can determine, hey, am I on this real CPU that actually has that bug and behaves not according to the specification, the official processor specification, or am I maybe in an environment where it's either a newer version of the processor or a VM where they have faithfully implemented that spec, and so the bug is not present. Or unfaithful emulation, where you see, since an emulator is a software piece that tries to implement the functionality of a hardware, like the CPU, sometimes there are slight differences or bugs that can be detected, and there's a nice paper on how to automatically actually detect these differences. And recently we've seen a lot of malware using more obscure math operations or floating point operations in the hope that the emulator doesn't support them, and if the emulator doesn't support these math operations, then you know that you're not running a real system but on an emulator. So there are some tricks in which you have to make sure that your emulator or your VM is faithful, although the general question remains, especially with more and more use of virtualization, can you really assume that you are in an analysis environment just because you're in a VM, right? That might not be enough anymore, because a lot of people use virtual machines for legitimate purposes, so if you can just detect if you're in a VM or not, it might not be enough to decide for a piece of malware that you're actually not in a victim environment. So what you want is, you might want to detect the actual analysis engine. For example, in the case of Anubis, a lot of other sandboxes, especially if they make available the reports that they generate, malware authors create little programs that check, for example, for the Windows product ID, or if there's a specific username used, or processes names, or hard disk names. Or you can check, okay, how many people have logged in since that machine is rebooted? How many people, or when was that machine rebooted last? So there are a lot of checks you can do that that look a certain way in a real environment, but not necessarily an analysis environment where you say no users are logged in and the machine was just started two minutes ago, right? That might give it away. You can check for unexpected DLLs that are loaded or mutex names. In Anubis, actually, we had a fun case where they were fingerprinting our background, sort of the pixel by pixel color of the background of our analysis system, and they said, okay, well, these guys always launch a DOS box at this particular location, so if this pixel is yellow, this is red, and this is black, I know that I'm in Anubis and I'm not just doing anything, right? So very sophisticated checks, presence of enough RAM, a 3-button mouse, the keyboard layout, a lot of checks that you can do, and malware authors do them, so here's sort of a reverse engineered code where you can't really see it very well, but they basically check for VMware or QAML for those strings present in hard disk names. There's even on forums, you can see the attackers share interesting tidbits. For example, a very old way to detect Anubis was to check if the user that was logged in, his name was Andy, because Andy was a PhD student who built the system and he just created an image with that name. So, we changed it to administrator, but, it's a check that they can do, and you see a number of other checks for usernames here or for the fact that the sample that you execute is called sample. So a lot of specific checks that malware authors can do, especially if they have access to your box. If they can study your box, they can specifically look for these environment values that might give away that the program is being analyzed in that specific environment. All right, so the third way, and sort of different rather than what I just explained, is to avoid monitoring altogether. So make sure that there is no malicious code executed in the sandbox, or you execute it in a way that the sandbox doesn't see it. And so a classic is, okay, so you wait for the user to click on something. And of course, some modern sandboxes have user interaction simulators. They will click on things. But, as our competitor recently published a blog post, sometimes you must click more than once. So you must click 3 times before some malicious activity happens. So, there's always this sort of arms race here. You can do things only after reboot, although you see in the sandbox that the program makes itself persistent. You can run only after or before certain dates or on specific dates, going back to the Michelangelo virus 20 plus years ago, a trick that still is in use. And then there are a couple of other ones that I want to just point out that we recently found that are fun, that use sort of quirks of different sandbox implementations. So this is just you can't read the code very well, but basically he does an if statement that checks if the time is after 2012, and I think it was January. So simple date-based checks that malware authors introduce into their malware. So the couple of things I wanted to point out is this one. This was fun. So if you monitor a process, you basically say, okay, there's a malware or potential malware process, and it might spawn other processes, and you add that to the list of processes that you monitor, and so you track all the things that the initial malware process and sort of its children might do, or if that malware injects code into a remote process, then you want to add that process to the list of things you monitor. Now, at one point, you want to stop monitoring, and you typically stop monitor when someone calls exit, right? The process exits, and actually the system call that you care about is NT-terminate process. So at one point we had the problem that, okay, after NT-terminate process, we thought, well, the process is now over, so why should we care about it anymore? So the interesting problem, and this is actually source code, it's not from the real Windows kernel, it's taken from ReactOS, shows you that you have this thing here where it says NT-terminate process is being called as part of exit process, and it says kill all the threads, and this is sort of where we stop monitoring. But unfortunately, one line later it calls loader shutdown processes that unloads DLLs, and as part of this unloading of the DLLs, some code is executed in those DLLs, and we would have already unhooked our monitoring, because actually on the last line you see another call to NT-terminate processes where it says first kill all the threads, and then now let's do it again. And unfortunately, in between, there is some chance for DLLs that malware authors might write to actually inject code and run this code. So, you have to sort of fix the way you monitor. Another classic that, affects sandboxes that do hooking is hook bypassing. It's basically, instead of jumping to a function, here I think it would be and adjust token privileges, you're actually not jumping into the start of the function, you are basically copying parts of the functions that this process would do before you actually jump there, so you execute a few instructions before, and then you jump in the middle of that function. And if you have a hook at the beginning of that function, or if you monitor the address that starts that function, then the execution will actually never go and hit your hook or hit the address that you're interested in, but it will just bypass it, but still execute the normal code that the malware authors want to execute. So, an interesting way of bypassing in-process hooks, typically of library functions. Another way is you can sleep. The classic sleep is, malware, you can only run it for so long, so why don't you just call a sleep 5 minutes, and after, the 5 minutes, presumably you have hit the timeout. And of course, guys who write sandboxes know about this, so they say, okay, why don't we just skip all sleeps that are longer than, 2 seconds, and just pretend that the thread has slept for the 5 minutes. The malware authors reacted to that by doing things where they start 2 threads, one sleeps and then calls terminate process or exit, and then in the second thread they would copy and restart the program. And so if you if you accelerate over the first sleep too fast, the actual process is being killed, and the second thread cannot complete copying and restarting the program. So you basically have killed the program, exploiting a race condition. A similar one is where you say sleep and then delete the file, and another thread is actually trying to execute that file. And again, if you accelerate over the sleep too fast, then the file is already gone when the second thread wants to start that file, and so the execution fails. So that's already somewhat tricky, but you can do it even more tricky by not just invoking any kind of system call, because, remember, system calls are something that every sandbox can monitor, but what if I want to stall the execution without actually invoking any system call or doing race condition tricks? In this case, I could go into a loop, a sort of do-nothing loop that just wastes time, and that hopefully is written in a way that it is slower in the execution environment that is the sandbox compared to the real victim environment. So maybe if it takes a few seconds to stall execution in a victim environment, it might take minutes, maybe even hours, depending on how you implement the sandbox, on your sandbox to get through this stalling loop, and before anything of interest happens afterwards. So you're sort of stuck with the problem that code is running, you don't know what's going on if you don't have deep insight into the execution of the process, and you might just conclude after a timeout that this program is benign because it didn't do anything bad, when in reality all it was is actually waiting you out and then continuing with bad operations afterwards. So, a tricky question of how to handle these stalling loops, and you cannot just accelerate sleeps because there are no sleeps. It's just running loops. All right, so by now you might already be depressed and think like, hey, this is bad. They have all these tricks. They use all these tricks. We're failing, and this great idea of running things in a sandbox and seeing what it does to detect previously unknown malware doesn't actually work. So it's a problem, but we believe that if you actually have the full visibility that I was talking about in the first part, there are certain things you can do to combat general classes, generic ideas of bypassing or detecting the presence of a system. So combating evasion. And I think we should sort of distinguish 2 things. One is triggers. The malware reads something from the environment and contains a check. And many of the things that I've told you are like that, right? Read this. Is this file present? Do we have the current date? Is this registry key present? Do we have a 3 mouse button? Do we have that memory, right? All this is system call. You acquire information. You compare that information with some values. And you do something based on these checks. right? And I'll call these checks triggers. So if there is some generic way in which we can detect those triggers and at least pinpoint that they are interesting and unusual, then we actually have a good chance to handle large classes of those automatically. And then there's another problem, that of the stalling loops. It's different because there are no checks. But the question again is, can we leverage deep insight into the execution of a program to actually recognize potential stalling and maybe skip it or accelerate it? Right? So these are sort of the two problems I want to use my last 10 plus minutes to talk about. All right, so first, bypassing triggers. The idea is you basically want to understand what malware does with interesting values that it might read from the environment, right? So malware goes and might read the current date. Malware goes and might read something from the environment that tells you how many buttons your mouse has. And then you want to understand if the data that has been read in such a fashion is used in a trigger, is used in a comparison operation, is used in a check inside the malware. And if you can recognize that, then at least you learned that there's some interesting check. And that, depending on how common those checks are or how infrequent they are, you can actually use that as a signal that this is bad. It's something that tries to detect you, that tries to evade you. And in the best of all worlds, you can actually go and explore a multiple execution path. You can explore alternate reality where you say, okay, the malware checks how many mouse buttons I have. I gave it 2 mouse buttons. It did that. It exited. What happened if I had given it 3 buttons, because that's exactly what it's checking for. And then let's see what it does if we give it that number of buttons. So that's sort of the basic idea. And what we need for that basic idea is we need to be able to track interesting inputs. We already sort of have the ability to do data flow tracking. Some value is read into memory and then it's moved around by instructions, move, whatever. And then there's a compare operation. So can we track this interesting data and can we detect that there's a control flow decision, a check, a trigger that uses that input, and then in the best of all worlds we are taking a snapshot and we are actually saying, okay, let's now let the program continue and then let's go back, let's revert to that snapshot and let's explore an alternative reality and let's explore the alternative execution path. So just to give you a few ideas about this, okay, we already know how to track input. If we have this deep visibility into the process, we can basically track every instruction so we can see if the program moves around data or operates on data. We can, of course, take snapshots. We have full visibility into the memory. We have full visibility into sort of the execution state, so we can just save the content of the virtual address space. And if we want, we can restore it by overwriting it back. And we can then basically explore alternate path by saying, okay, memories move to certain instructions and now they are used to compare, I don't know, a value with 15. We can say, well, the value that the program currently has is 0, so let's continue to let it execute, but then revert and pretend that that value had been 15 and explore an alternative path. So, that sounds good. There is a little bit of complexity. I don't want to go too much into detail. I just want to sort of give you the gist. The complexity is that of inconsistent values when you just fix up the value in one comparison operation. In this particular case, malware reads a value x, multiplies it by 2, adds 1 to get the value y. So this is this. Let's assume it reads 0. Then it multiplies that by 2, so it's still 0 plus 1, so you add 1, and then you pass that value 1 into the check function. And here you check if is the value that I read and that I multiplied by 2 and added 1, is it 47? And if not, then you exit, right? And so what you get here is, well, we know that the malware checks on some kind of input, and apparently it then exits. So we can go and say, okay, magic is 0, we exit. If we would set magic to 47, well, we would pass. But the problem is, just by making this check pass, by setting magic to 47, we actually did not correctly adjust the other values, x and y. So if program continues then to execute, in this case it would just print out x is 0. when in reality it should print out something else. It should actually print out x is 23, because only if x is 23, then y will be 47 and magic would be 47. Okay, so you basically have to track the input in a clever way, in a sense. So whenever you copy values around after they've been read from the environment and they are manipulated by the program, you actually have to remember how they have been manipulated and then adjust them accordingly. So we call this a constraint set. You basically say, okay, x is the input, y is dependent on x, which is dependent on the input, magic is equal to y. So if we want to solve the equation and want to say, okay, we want magic to be 47, so we can then use a constraint solver or some simple linear algebra solver, depending on how complex you want to go, and it actually solves you and gives you the output that x should have been 23, and in this beautiful case, we would actually learn that, hey, the program expects that input value, and only if that input value is given, it would reveal additional behaviors later on. So it basically, would have done both things. It would have told you, hey, there was a check, and hey, we can solve that check, and we would even learn something about the input that would have been necessary to drive the program down. That's not always possible, of course, because you can imagine, let's say, an input is being hashed, and then the result of that hash is compared. So you would have to invert the hash function to learn what the right input would have been, which is presumably hard or impossible. So in this case, you only know that a check has happened. But you can basically learn all these checks, and you can know that programs do checks based on interesting inputs that you can define, and you can handle this entire class of possible evasions by just finding interesting inputs that the program manipulates or checks for in an unusual fashion. And we find this is a very powerful way of handling trigger-based malware. Let me just give you a couple of minutes the high-level idea on the second part, which is the stalling loops. So stalling loops, I said, they are difficult because they don't have a trigger, right? There's no input being read, there's no system call that happens, there are no tainted inputs that we need to track. It's just a program looping and spinning and not doing anything. So how can we detect that? Again, the cool thing is that we have this deep visibility into the process. We can actually sort of inquire the process and say, what are you doing right now? And then, you do that second after second after second, and you find out, hey, it's always in this loop. And it doesn't seem to actually do much. The system calls that it invokes are maybe irrelevant, or they all fail, or they all succeed, but actually don't change the state of the system. So you can recognize that it's doing something, but it doesn't actually make progress. And when you learn that it doesn't make actual progress, then you can do two things. First is you can try to reduce the overhead that you produce by logging or monitoring that particular loop. And maybe you get fast enough so that the program will just go out by itself. Or you can take a more active approach and actually actively interrupt the execution and say, hey, I just want to jump out of that loop. Okay, so this is just sort of high level. I think I'll, given that I'm sort of short on time, I'll have to let you read the white paper or the presentation, but there are basically a couple of things you can do to find the code blocks for which you should reduce logging, as well as how to actually interrupt the loops once you find them, and reducing the logging is not sufficient. Okay? But so what is nice about it is, again, this idea that deep visibility enables you to see things that are necessary to combat something that malware authors already do, and that they successfully use to bypass sandboxes that are not prepared to react to this kind of evasive activity. Okay, so going to the conclusion, I just want to leave you with one other thought, which I thought was interesting, and that is history repeats itself. So we've seen for malicious binaries, we've seen that, bad guys write viruses, AV vendors write signatures, malware becomes polymorphic. That means, changes the way it looks on disk, changes the way so that you cannot recognize it using static signatures anymore. So people introduced dynamic analysis environments, sandboxes, and now the next step is of the malware authors to try to avoid and detect sandboxes. And the thought here is that we actually see something very similar also on the web side of things with exploit toolkits, right? First, JavaScript exploits. You write simple tokens to detect them. They start to obfuscate themselves and use frequently eval and many levels of eval to hide the code from static signatures. And then people introduced honeypots, which are dynamic analysis environments for JavaScript. And now we actually see attackers introducing tricks into their JavaScript so they can recognize if they're executed not in a real victim browser but in a honey client. So it's sort of the same evolution from like simple signature-based detection, obfuscation, dynamic analysis, recognizing dynamic analysis, all over again for a completely different domain. So I thought that was sort of an interesting analogy. And I think I'm out of time, so with that I conclude. I think visibility and fidelity are two critical factors when building sandboxes, and we think full system emulation is a desirable spot in the design spectrum. I hopefully convinced you that dynamic malware analysis and evasive code is hard, but also that we shouldn't give up because there are general approaches in which we can counter evasive code. And with that, thank you very much, and open for questions.